Hello, and welcome to NetW 205. Today we begin with Chapter 1, and there's going to be 11 chapters this semester. We're going to be talking about uh, LANs, switching, and routing together. So you'll understand how LANs work. You're going to be able to create VLANs, secure a switch, do inter-VLAN routing, and we'll talk about routing, RIP2, OSPF, and EIGRP. So we got a of full semester of hands-on labs. That's what we're going to be doing. So every time we come to class, be prepared to work. So we're going to be working together on packet tracer in class, and then we're going to be working together on the physical equipment, setting up labs. So please pay attention to the lecture, and I want you to answer questions when I ask you to, like I told you last time, and submit them in eCollege under the basket. Go to the Dropbox, and you put it under the basket homework for that week. All right. So week 1, for example, we'll be covering chapter 1 and 2. All right, let's start, and we'll talk more about exactly what we're going to be doing in class when we meet. All right, so today we'll start with introduction to switch networks. So we'll start with the switching first. So you'll learn how to design a LAN, what it takes to design a LAN, and we'll review some of the content switched material that we covered last semester in that W203. All right. So when we talk about the complexity of networks, if networks grow and hopefully they keep growing within a corporate environment if the company is expanding. So switches are going to be the central concentrator that interconnects all the hosts inside your LAN. And now you are adding voice over IP devices that are going to be connected in there. Sometimes you may be sending voice, not only voice, video, and of course data, and applications, grow in capacity. So the ports have to be, the speed has to be very fast, and they have to be secured as well. So as they grow, you want to make sure that your LAN, the design of your LAN is very, very um, easy to expand, very secured, easy to troubleshoot and maintain, and so on. So we'll discuss all of that as we move along. Okay. Now, what is a converged network? In the old days, in the early 1990s, or not even in the 1990s, late 1990s, we were even in the early 2000s. We had, if you wanted to get phone service, you have to call a service provider. If you wanted to get the internet, you call a different service provider. If you wanted to get TV services, you would have to call a different service provider. But now we converged all of these three separate services into one onto one line. That's what a converged network. That's where you send data, voice, data, and video on the same wire. That's cheaper, less expensive for the provider because all they have to do is use one equipment, sending all the data on one line. This is like FiOS or your cable TV that is coming into your home. And supposedly it gets cheaper for us, less expensive when you have a converged network. Now you need to be able to support all of these. All of these different services, they all travel on IPv4 packets or IPv6 packets. You can have that. Eventually, that's what's going to happen. So it's a lot more simplified than just having three separate services coming into your house on three separate wires. All right, so you have to be able to support the three different types of services that are converged onto that one medium. Um, Cisco has been working on and has achieved a milestone in terms of the Cisco Borderless network. That's when they allow anything to connect to anything that they want. Your phone connecting to your car, your refrigerator connecting to your phone, and your TV, your remote, everything within you could have all of that on a smart device in your hand, and you'll be connected to anywhere, to anyone at any time. Security, reliable, and seamlessly. And So that's the Cisco Borderless network, and there's many devices that they have available to support all of that, and they need IT techs such as you to support and troubleshoot and maintain these devices to make sure everything is connected and where they're supposed to be. For example, their network, the way the borderless network works, number one, it has to be hierarchical, which means the way you design your LAN has to be in a tree method. You got the core on the top and the tree branches go down. Okay, we'll discuss the three levels of the hierarchical LAN design in a few minutes. It has to be modular, which means it's easier to expand. Can you just add switches, ports to a big module that you have? It has to be resilient. You have to have some redundant parts to it in case like redundant links, maybe in case a link breaks or even a switch break goes out. You have the network is supposed to adjust and keep the users connected. And of course, it has to be flexible, not very complex, especially when you are troubleshooting, right? So here is a typical converged network. The three layers of the LAN, of the designing of a LAN, is the core, the distribution, and the access layer. So the core is the center. That's where everything goes, okay? And so let's say this is the headquarters. Everything goes into the headquarters, and then the headquarter of the corporate sends the data to a distribution layer. For example, let's say this is the Northeast, and then the Northeast, you could have several branches coming in. This is the Northwest. You have several branches coming in. This is where no users are populated at the distribution or the core layer. Users are populated at the access layer. Okay. So those are the three designs. For example, let's say if this was a campus, will be the core of the building that everything comes into, and then you send this to the engineering. This you send to marketing and sales. This goes to distribution, whatever, different. This goes to research and development and data. It could be a campus, it could be a corporate. Now, in the engineering, you may have several different access level where you have the electrical engineers connected, has their own access. You may have the software engineers on another access layer, and you may have the mechanical engineers or something like that, right? So at the marketing access, you may have marketing and sales on separate LANs. Those are at the access level. At the access level, that's where you have the users. So if the users want to access their email, for example, well, you may have an email server just for the marketing and sales. So you place that email server at the distribution layer right here. If you have an email, for example, for the whole company, you can put that email server at the core layer. So people from the engineering can go out and get to their email at the core layer, but that's not recommended. I mean, you could do that too. I mean, for easier purposes. The idea is to break this down in a tree method and a hierarchical method is that you should be spending 80% of the time in your LAN and only 20% to go out to a different LAN to communicate. So the 80-20 rules, and that's how you can control traffic. So question number one, what are the hierarchical three-layer method or design that you would use in a LAN? And the answer is the core, that'll be the top layer, the distribution layer, and the access layer. All right, so the switch network is used to allow traffic move very quickly. A switch is in there. That is the central point where everyone connects to. So when a user sends data to a port on the, every user is connected to a port on the switch, and when the switch receives a frame from an incoming device, it looks up the destination MAC address that's stamped on the frame, finds out which port you're going to, and sends that that sends that frame directly to that other port automatically without even stopping in most cases. So a switched LAN allows more flexibility because, as we will see later on when we create VLANs, we can move ports around from one LAN to another, and you don't have to even purchase more switches if there is no need to. Um, of course, when you're creating more LANs and you move frames as quickly as possible, traffic management is easy. You isolate traffic much easier that way, and you can support quality of service, which means, if you remember from last semester, QoS means that you are allowing the switch to set priorities to frame additional securities to the port. You can set up wirelessly IP telephony on there and any mobility services. So switches nowadays allow you to do all of that inside one local area network. Now, if you go out and purchase a switch, what do you look for? Do you look for fixed platform, which means once you have number of ports, let's say you have 24 ports or 48 ports, you cannot expand beyond these number of ports. It all depends on how many users you have. Do you want them to be module? That means you are going to take a module and then add the ports inside. You add more and more chassis, line cards inside the switch itself. This is a little bit more expensive. This is, you're thinking of expansion later on. Okay, sorry about that. Let me just continue. You may choose to have stackable switches, which means if you can buy another switch and daisy chain them, as you can see from here. So you could do that if you want to. But most switches are bought in fixed mode. Now, a switch makes a decision based on the ingress and destination port. So depending on which port you are coming from, the switch is going to remember which port you are coming from and which port you're going to, right? So when you're coming, he knows your source source MAC address, and he knows which port you are coming from, and he writes it in the MAC address table. Then he looks at the destination address, looks at the MAC address table, and finds out where you're going, and then sends that frame to that port only. So it keeps a table of all the MAC addresses and which ports they are located at. So every frame that comes in, I just send them to his port, only to that port. All right. Now the switch dynamically populate the MAC address table, so you don't even have to do anything. The MAC address table is called Content Addressable Memory, the CAMP, or we just call it the MAC address table. I call it, it's much easier that way. So the best way to think about it is here. Let me see if I can get a packet tracer up and running. Let me see here. Let me see, where is my packet? Let me get a packet tracer going and I'll show you what I'm talking about. So if I get a switch, a 2960 switch right here, and any frame that comes into the switch, let's say came at port 01, and your frame, your MAC address, let's say it's A, then I know MAC address A is located at port 1. Then I'll place that MAC address in the MAC address table. And then I look at the destination MAC address. If it's, and then I look up the MAC address table. If it's not there, then I know it's going to be here. You know what? Let's do this. Let me go to the end devices. I'll put a PC here and a PC here, right? And let me connect these devices together. Here's fast Ethernet 0 to fast Ethernet 01. Let's take this to fast Ethernet 4 and put this on fast Ethernet 0. All right. These two guys are on the same LAN. So let me give them an IP address 192.168.10.1. You don't need a default gateway because there's no router. Leave it at /24 as their subnet mask. Okay, let's go to PC2. Go to the desktop and type in 192.168.10.2. Okay. Now, if I ping, let me go to the switch itself, go to CLI. I want to show you something. If you type EN and just leave it the way it is, let's just show MAC-address table. There's nothing in there because we did not communicate with anyone. Now, if I send the ping command to PC1, what's going to happen? He is going to show me the, first of all, let's find out what his MAC address is, PC1. So if I go to the command prompt and type ipconfig/all, and I see the MAC address here for my PC is, I think it's 009-7C97B819, if I'm not mistaken. Just try to remember that. Okay, B819. Let me go to PC1 and type ipconfig. Oh, I type ipconfig-t. ipconfig/all. And 1A4B is the MAC address. Here's what's going to happen. When I send a ping, when I ping PC1 and PC1 responds back, the switch is going to know that this MAC address is located at port 1 and this MAC address is located at port 4. Why? Because when I send in a frame, he has to stamp his MAC address as the source, and he knows it's coming from 01, so he puts them in that CAM. And when he responds back, he knows he has to put his MAC address as the source, and he puts them in his MAC, right? And therefore now I have the MAC address table, the CAM, filled up. So right now the MAC address table is empty, but when I go in to PC0 and I ping PC2, which is 192.168.10.2, and I get a respond back, now the switch has dynamically learned the MAC addresses of both guys and the ports. So if I go back here and I hit the upper arrow key to repeat the command and hit enter, now you see that B819 is located at 01. That's the MAC address of A. And 1A4B, that's the MAC address of C. So he learned both MAC addresses. Now, if I'm ever going to send any data to PC1, I'll just look it up and I find out, I look at the destination MAC address of the incoming frame. I see that the destination MAC address and I send them only to his port. So they are dynamically learned. You see that? All right, now, if he sends a MAC address to somebody that he doesn't know, what is the switch going to do? He's going to look up the destination IP address. You know what? Let's do that. Let's do that again. Let's bring in another PC, and I'll put it right here, and I'll connect it, and I'll put them through port, let's say 11. Okay. Now, let's say let's give him the address also, by the way, 192.168.10.3. Okay. Same subnet mask address because you do have to assign them a level 3 IP address. Now, when I ping PC2, what's going to happen is he's going to look up first of all, he looks up the source IP address. He says, all right, I already have it in port 1. Good. Then I look up the destination MAC address, which is PC2 MAC address. He doesn't see it in the MAC address table. So what does he do? He floods the ports, sends it to both of them. PC1 he's not going to be able to recognize his IP address, his MAC address, so he doesn't respond back, but PC2 recognizes his MAC address on that frame, and he receives it. Then when he responds back, he'll be able to get it. Okay, so the MAC address table, as you can see right now, only has port 1 and 4 populated with these two guys. Now when I go, you can actually have PC2 ping. It doesn't have to be PC1. So let's go to PC2 and ping I'm sorry, PC1 ping PC2. So ping 192.168.10.3 and the reply, and I go back to the MAC address table and I hit the upper key to repeat the command, and now I got 4 and 1 got erased, by the way. Okay, that's because it only takes 7 seconds. Let me go in and now ping again PC1, and now we got 3 of it. Why was PC1 erased? Because you're only there for a certain amount of time in the memory. If you don't send anything out, you're taken out. That's aging. So that's something to remember. Okay. So question number 2: how does the switch learn populate the MAC address table? The answer is by inspecting the incoming source MAC address that is stamped on the frame and which port they are coming from. So I know that this is PCA coming from port 1. That means that's where I put them, number 1. Question number 3: what does the switch do when it receives a frame and it does not have the destination MAC address in the MAC address table? The answer is it does flooding. It sends the frame to all the ports except who sends the frame, except the one where it receives the frame from. Okay, question number 3. What happens when you do not send any frames to the switch? What happens is the MAC address will be taken out from the MAC address table if you do not communicate with the switch within 7 seconds. Okay, so you got learning, you learn the MAC address, you got flooding, and you got aging we talked about. And then the switch, once he has a MAC address table, he can filter out and sends data only to a specific destination. All right, so let's go back to our table. So now you learned a little bit about how the MAC address learns and populates the camp, right? There are 2 different switch forwarding methods. There's something called a store and forward, and there's something called the cut-through switches. Store and forward is where the frame comes in, the switch stores it inside, checks the frame out. Remember, when you looked at the frame, there was a CRC check at the end of the frame, and if the frame is good, that means it has not been corrupted on the way to the destination. Then the switch will pass that frame to the destination, send him on his way. Cut through means I'm not going to check to see if the frame is good or bad. I'm just going to look at your destination and send you to your destination as quickly as possible. I look at the destination MAC address and do it very, very quick. Okay, so here is a store and forward. It stores it inside and checks everybody, make sure all the data, the frame, everything is good before I send it out. And I double check the FCS number. Store and forward doesn't do that. There's no FCS check, no automatic buffering, nothing like that. As soon as the frame comes in, you send it right out. Remember the FCS number? The FCS number says that take a look at all the data and make sure it's good. So what you do is before you send your frame, you take the data of the frame, every bit, and you send it through a program, and that program takes a snapshot of how the data looks like and puts a number right here. So when you receive the frame, this is what the switch does, the store and forward switch does. He is going to take the frame, bring it inside, and then run the whole frame through the same program that the sender did. And the number that comes out still should be the same number that's stamped on the frame. If it's good, if it is, then that means that frame is good. Send them out. If not, drop the frame and don't send them to the destination. Cut-through switches doesn't even do that. It doesn't bother looking at the FCS. He just looks at the destination and sends them out and you cut right through. You go to your destination as quickly as possible. Okay? Collision domains. A collision domain is where a hub does, which means if you are going back, let's just go back to the switch right here in Packet Tracer, And let's assume that this is a hub. That means when I use carrier sense multiple access with collision detection, remember that from last semester? That means if A wants to send data to PC, if PC0 wants to send data to PC2, he goes into the hub and he sends to see if there's traffic. If there is no traffic, then he sends the data to everybody because the switch doesn't know whether it doesn't have a MAC address table. So that means if PC1 wants to communicate and then he comes in and he sees traffic, he has to wait. And that's not good. So that means this area is the collision domain. The more users that are attached to the hub, remember, assuming this is a hub, the more users that are attached to a hub, the bigger the collision domain, and that's not good. Of course, we don't want a hub. We want to use a switch. A switch has your own lane to anywhere you want. You don't even have to stop and look for traffic because the switch will make sure that you have connection to your destination because it has the software to find out where you're going and sends you on your way. So when he is communicating with PC2, PC1 can go into the switch and the switch will allow him to communicate with someone else. So they have their own collision domain, their own lane to their destination. Okay? All right, so that's what collision domains are. Okay, let's go back. Let's see. So we definitely do not want to be part of a collision domain. Broadcast domain is a LAN itself. So that's what a logical LAN is. So when a switch receives a broadcast frame, it sends it to everybody. That's flooding. Okay, so question number 3 or 4. 3. What is a collision domain? Well, there it is, a segment where devices must compete to communicate. And what is a broadcast domain? It's the extent of the network where broadcast can be heard. So switches creates one broadcast domain. And add to that definition is a broadcast domain is a local area network, is what makes a LAN. All right, alleviating the network congestion. If there's a lot of traffic coming into the LAN, what you're going to do is you separate the collision domain. In other words, put a switch instead of a hub. Full duplex communications, where you can send and receive data at the same time. Your NIC allows you to do that, so that makes it much easier. Buy switches with high port density. Has a lot of ports in it. So you can put a device on each port. Buffering large frames. You want to buy a switch with a lot of memory. High-speed ports. Gigabit ports will be the preferable way to go if you can afford that. All right. And of course, in terms of switching processes and having low cost per port is what's important. Gigabit and 10 gigabit Ethernet ports on the switches are pretty expensive, but if you can afford that, why not go for it? All right. And I wanted to let's see. Let me see if I may want to make sure that I covered everything. Yeah. So that's it. Easy chapter. We'll talk about more of switching in chapter 2. So until chapter 2. Just read your chapter. This should be a very small chapter to read to get you going. So please read the chapter, answer the questions that I told you about, and we'll take it from there. Hold on a second. So until next time, when we meet in chapter 2, God bless.